An Introduction to Semiconductor Materials. Welcome to this presentation on semiconductor materials, essential building blocks of the digital age. At the heart of modern technology lies silicon, a semiconductor that powers nearly every electronic device we use today. From smartphones and laptops to data centers and smart sensors, semiconductors are the silent engines driving innovation forward. This journey begins with silicon, abundant, versatile, and highly engineered. Silicon enables the development of devices that power the digital world, forming the core of integrated circuits, memory chips, and processors. These devices, in turn, serve as the foundation for groundbreaking innovation across industries, from communications and computing to healthcare, transportation, and artificial intelligence. As we move forward, understanding the role of semiconductor materials is crucial for grasping how today's digital capabilities are made possible and how tomorrow's innovations will continue to emerge from these remarkable materials. Definition and key properties of semiconductors. Semiconductors are defined as materials with electrical conductivity that lies between conductors and insulators. They don't conduct electricity as well as metals like copper or silver, but they're far more conductive than materials like glass or rubber. This intermediate behavior allows for fine control of electrical signals. On the conductivity spectrum, conductors sit at the high end. Examples include copper, silver, and gold. Insulators, such as glass, rubber, and plastic, reside at the low end. Semiconductors like silicon, germanium, and gallium arsenide fall in the middle. Key properties make semiconductors special. They offer controllable conductivity, are sensitive to temperature, respond to light, and can be controlled with voltage. These features enable the creation of transistors, sensors, LEDs, and solar cells. A helpful analogy is water flow. Conductors are like wide rivers. Semiconductors resemble narrow streams, and insulators act like blocked dams. This unique positioning is the foundation of modern electronics. Where semiconductors fit in the conductivity spectrum. Semiconductors occupy a distinct position between conductors and insulators on the electrical conductivity spectrum. At one end, conductors such as metals have high conductivity and allow electrons to flow freely with minimal resistance. At the other extreme, insulators like rubber or glass resist electron flow almost entirely. In between these two lies the unique and valuable space where semiconductors operate. What sets semiconductors apart is their controllable conductivity. They can behave like insulators under certain conditions and like conductors under others, depending on external inputs such as voltage, temperature, or light. This ability to switch behavior is what enables digital logic, memory storage, and signal processing. By understanding their place on the spectrum, neither fully conductive nor fully resistant, we see why semiconductors are essential. They allow engineers to build electronic systems that can amplify signals, perform computations, and store information reliably and efficiently. Comparing conductors, semiconductors, and insulators. To understand the role of semiconductors, it's helpful to compare them with conductors and insulators. Conductors allow excellent electron flow due to the presence of many free electrons. They offer very low electrical resistance and maintain stable performance across various temperatures. Common examples include gold, copper, and silver, all of which are used in wiring and circuit connections for their efficiency. In contrast, insulators block electron flow completely. They contain no free electrons and exhibit very high resistance, acting as stable barriers. Materials like glass, rubber, and ceramic are used in insulating layers, casings, and barriers in electronic systems. Semiconductors fall in between, with resistance that is variable and controllable. They can be turned on or off, are sensitive to temperature, and also respond to light. Examples include silicon, germanium, and gallium arsenide. These unique properties make semiconductors the bridge between conductors and insulators, enabling advanced electronic functions. Electrical properties of semiconductors. Semiconductors exhibit controllable electrical conductivity, which can be adjusted using doping and other techniques. Their conductivity is not constant. It varies between that of conductors and insulators. This variability is largely due to the presence of a moderate band gap, typically ranging from 0.1 to 4.0 electron volts, eV. The band gap determines how easily electrons can move from the valence to the conduction band. Through doping, engineers introduce impurities that either add free electrons or create holes, effectively enhancing the material's conductivity. This tailored approach allows for the precise control of current flow. Furthermore, semiconductors can switch between conducting and insulating states. This is the foundation of logic operations in digital devices. The ability to turn electron flow on or off, creating binary states of 0 and 1, makes semiconductors the basis of memory, processors, and virtually all modern electronics. Thermal properties of semiconductors. Semiconductors are highly sensitive to temperature, a property that significantly influences their performance. As temperature rises, so does their conductivity. This occurs because thermal energy excites more electrons into the conduction band, increasing the number of charge carriers. In warm conditions, semiconductors behave more like conductors. Conversely, at low temperatures, fewer electrons are excited, and the material behaves more like an insulator. This dynamic response makes semiconductors ideal for use in temperature sensors and thermal management systems. In real-world applications, heat generation must be carefully managed to prevent device failure. For example, CPUs and power electronics rely on thermal control systems like heat sinks and fans. Designers must also consider how temperature variations affect conductivity to ensure reliable performance under varying environmental conditions. Understanding this thermal behavior is essential for optimizing device function and lifespan in both consumer and industrial electronics. Optical properties of semiconductors. Semiconductors interact with light in versatile and powerful ways, enabling a wide range of optoelectronic applications. These materials are sensitive to light and can absorb it, converting photon energy into electrical current. This is the working principle behind solar cells. Conversely, when electric current flows through certain semiconductors, they emit light, forming the basis for light-emitting diodes or LEDs. Additionally, semiconductors can detect light and convert it into signals, which is how image sensors and photodetectors operate. This interaction with light opens up vast opportunities in fields such as renewable energy, communication, and imaging technology. For instance, in fiber optic communication, semiconductors help emit, detect, and modulate light signals. In solar panels, semiconductor layers are engineered to maximize light absorption and conversion efficiency. By designing semiconductors with tailored optical properties, engineers can create devices that harness or respond to light with high precision and efficiency. Fundamental characteristics that make semiconductors essential. Semiconductors possess three interconnected characteristics that make them indispensable to modern technology. First is the combination of electrical and thermal properties. As temperature changes, the electrical conductivity of a semiconductor changes as well. This allows precise control over switching behavior, a key function in processors and logic circuits. Second is the interaction between electrical and optical properties. In some semiconductors, light can generate electricity. This is the foundation of solar cells. Conversely, electricity can produce light, which is the principle behind LEDs. These optical-electrical interactions are crucial in communication, sensing, and display technologies. Finally, when electrical, thermal, and optical properties are combined, semiconductors enable the creation of complex, multifunctional devices such as smartphones, image sensors, and solar panels. These three properties work together to support dynamic, responsive, and efficient electronic behavior. Their integration enables the versatility and functionality that define today's digital tools and tomorrow's innovations. Semiconductor materials and their unique properties. Semiconductors power the digital world through a variety of materials, each offering unique strengths. Silicon dominates the industry with 95% market share. It has a band gap of 1.12 electron volts, offers stability up to 150 degrees Celsius, and is cost-effective. These properties make silicon ideal for CPUs, memory chips, and solar cells. Germanium, with a 3% share, was a historical pioneer. It has a lower band gap of 0.67 eV and features high electron mobility and strong sensitivity to infrared light. It's used in RF devices and IR detectors. Gallium arsenic accounts for 1% of the market and is known for its high performance. With a 1.42 EV band gap and a direct band structure, it supports ultra-fast switching in applications like RF, microwave, and LEDs. Lastly, wide bandgap materials like silicon carbide and gallium nitride with over 3 EV band gaps are emerging as future solutions for high-temperature and high-power applications, including electric vehicles, 5G, and power conversion. Semiconductor material comparison. Choosing the right semiconductor material depends on several key factors: band gap, carrier mobility, cost, temperature tolerance, and intended use. Silicon, with a 1.12 electron volt band gap, offers medium mobility, low cost, and can operate up to 150 degrees Celsius. It is widely used in digital logic applications due to its reliability and affordability. Germanium has a lower band gap of 0.67 electron volts and high mobility, making it responsive and efficient for RF and infrared technologies, but its operating temperature is limited to 85 degrees Celsius, and it is more expensive. Gallium arsenic features a higher band gap of 1.42 electron volts, very high mobility, and can function up to 300 degrees Celsius. It's ideal for high-speed and microwave devices. Wide bandgap materials like silicon carbide and gallium nitride, with band gaps over 3 electron volts, operate at temperatures above 600 degrees Celsius. Though costly, they excel in power electronics, RF, and electric vehicle systems. Each material's strength serves specific technology needs. Energy band theory and electron behavior. To understand how semiconductors work, it's important to explore energy band theory. In atoms, electrons occupy energy levels. In solids, these levels form two main bands: the valence band, where electrons are bound, and the conduction band, where electrons are free to move and conduct current. The region between them is the forbidden zone or band gap. For silicon, this gap is about 1.12 electron volts. Electrons must gain enough energy to jump this gap, from bound to free. This process involves 3 stages. First, electrons are in the bound state. Second, energy input causes excitation that breaks bonds. And third, electrons enter the conduction band, enabling current flow. In conductors, there's no band gap. Electrons move freely. In insulators, the gap is too large, so current is blocked. Semiconductors have a small, tunable gap, allowing controllable conductivity, an essential property in all electronic switching and processing devices. Activation energy in semiconductors. To enable conduction in semiconductors, electrons must gain enough activation energy to cross the band gap from the valence band to the conduction band. This activation can happen in 3 main ways. First, thermal energy, or heat, provides energy that excites electrons, helping them make the jump. As temperature increases, more electrons become mobile, boosting conductivity. Second, light energy can also activate electrons through the photovoltaic effect. Photons, particles of light, strike the material and transfer energy to electrons, promoting them to the conduction band. This is how solar cells generate electricity. Third, doping involves intentionally introducing atoms into the semiconductor to create extra charge carriers. These added atoms provide easier paths for electrons, making conduction more efficient. Together, these methods make semiconductors smart materials with controllable conductivity. Because of this tunability, semiconductors are ideal for applications like electronic switches, amplifiers, sensors, and power devices. Their flexibility drives innovation across the electronics industry. The global impact of semiconductors. Semiconductors are everywhere. They power the digital world around us, from handheld devices to large-scale infrastructure. Their global penetration is unmatched. Virtually all modern electronics, from smartphones and laptops to cars and industrial robots, rely on semiconductors. This deep integration fuels a massive market value, with the semiconductor industry generating an annual revenue of over $574 billion. That number continues to grow as digital transformation accelerates across all sectors. Daily usage is also staggering. Over 50 billion semiconductor devices are used worldwide each day, enabling communication, computation, sensing, and control across our lives. Beyond technology, semiconductors are an economic engine. The industry supports around 8 million jobs globally, ranging from research and design to manufacturing, sales, and service. The scale and significance of semiconductors make them not just a technological cornerstone, but also a major driver of global innovation, connectivity, and economic growth. Real-world applications of semiconductors. Semiconductors power nearly every industry around us, driving innovation from personal devices to global infrastructure. In the consumer sector, electronics like smartphones, laptops, TVs, tablets, and gaming consoles rely on semiconductors, each device containing 15 to 50 billion transistors. In automotive applications, modern vehicles use over 1,000 chips for engine control, infotainment, safety systems, electric vehicle powertrains, and GPS navigation. In the energy sector, semiconductors enhance efficiency in solar panels, LED lighting, inverters, and smart meters, reaching up to 22% efficiency in solar energy conversion. In medical technology, semiconductors power life-critical tools such as MRI scanners, pacemakers, digital X-rays, and blood monitors, ensuring precision and reliability. Telecom depends on semiconductors for 5G networks, fiber optics, data centers, and satellites, supporting 99.9% uptime in global connectivity. Finally, industrial manufacturing uses chips in robotics, IoT sensors, motor control, and AI systems, enabling the transition to Industry 4.0 and smart factory automation. Semiconductors truly are the backbone of modern progress. Semiconductor Revolution Timeline. The evolution of semiconductors has shaped the modern digital age, step by step. It all began in 1947, when Bell Labs developed the first transistor, laying the foundation for modern electronics. In 1971, Intel introduced the first commercial microprocessor, the 4004, sparking the computer revolution and enabling programmable logic. By 1995, the Internet boom brought a wave of web-enabled devices, creating an explosion in data traffic and semiconductor demand. In 2007, the smartphone era began, bringing mobile computing power into everyone's pocket and further increasing the need for smaller, more powerful chips. Moving into 2020 and beyond, semiconductors now drive AI and IoT, the era of smart everything. From smart homes and wearables to autonomous systems and predictive analytics, semiconductors have become the invisible foundation of our connected digital world, enabling innovation and transforming industries in real time. Semiconductor Market Forecast. The semiconductor revolution is far from over. In fact, it's accelerating. Looking ahead to 2029, the global semiconductor market is expected to experience strong growth, with an impressive 15.2% annual growth rate. This expansion will be fueled by the explosive rise in connected devices, where the concept of the Internet of Everything becomes reality. From smart homes and wearable tech to autonomous vehicles and industrial IoT, nearly every aspect of daily life and infrastructure will be connected through semiconductors. In parallel, semiconductor technology is advancing at the atomic level. New process nodes are pushing the boundaries of atomic-scale engineering, enabling faster, smaller, and more power-efficient chips. These innovations will be essential for artificial intelligence, edge computing, and next-generation connectivity, like 6G. As the demand for intelligent systems grows, so does the need for advanced semiconductor solutions, cementing their role in shaping tomorrow's digital world. Emerging frontiers in semiconductor technology. The future of semiconductors is being shaped by bold innovations across several emerging frontiers. First, quantum computing aims to go beyond classical limits using qubits, superconductors, cryogenic systems, and error correction. The goal is to achieve over 1,000 qubits by 2030, unlocking unimaginable processing power. Next, AI chips are revolutionizing neural processing with specialized architectures like neuromorphic designs, TPUs, and NPUs. These chips power edge AI, operate with low power, and can deliver up to 1,000 times greater efficiency than traditional CPUs. In parallel, 6G networks are being developed for ultra-fast, low-latency communication. Technologies such as terahertz signals, brain-computer interfaces, holographics, and zero-latency connections aim for peak speeds of 1 terabit per second. Finally, green tech is ensuring sustainability through carbon-neutral manufacturing, recycling, bio-based materials, and energy harvesting solutions. The target is to reach net zero emissions by 2050. Together, these frontiers will transform not just technology, but also society. The semiconductor era and future roadmap. We are now living in the semiconductor era, where progress in computing and electronics shapes every part of our lives. The technology roadmap ahead is bold and ambitious. By 2025, we expect mass production of 3-nanometer chips, pushing boundaries in performance and energy efficiency through advanced packaging. By 2027, we move toward quantum advantage, with commercial quantum applications that outperform classical computers in select tasks. In 2030, the rise of AGI chips, capable of human-level artificial intelligence, could redefine learning, automation, and decision-making. Looking further to 2035 and beyond, molecular computing may emerge, enabling processing far beyond the capabilities of silicon. Semiconductors are not just components. They are the invisible foundation of human progress. They enable endless possibilities, global connectivity, and future innovation. As we move forward, semiconductors will continue transforming how we live, work, and connect, with greater intelligence, speed, and sustainability than ever before.